Hello, everyone. Welcome back. Today, we're going to be discussing the gas laws that can be used to predict the behavior that you're going to see in gases when you make particular changes. Okay. So, the four things that dictate how a gas is going to behave is the pressure, temperature, volume, and how much of it you have. Okay, which is number of moles. Okay, today we're going to learn how these things are related. Okay, there are various relationships. There's relationships between volume and moles, pressure and moles, temperature, and everything. Okay, there's different relationships, and it all eventually comes into the ideal gas law, which we're going to talk about tomorrow. But for today, we're going to talk about how these things are related independently. Okay, and when we look at a relationship, we assume that everything else is constant. Okay. And there are four laws total, okay, derived from four different scientists. You have Boyle's law, which looks at pressure and volume. You have Charles' law, which looks at volume and temperature. You have Avogadro's law, which looks at volume and moles, and you have Lusak's law, which looks at pressure and temperature. Okay, so the first one we're going to look at is Boyle's law, which looks at pressure and volume. Now, when we're talking about pressure and volume, again, we are assuming that the other two are being held constant. So this is the relationship between pressure and volume when moles and temperature are kept exactly the same. Okay, so we are assuming that moles and temperature are exactly the same at all times. Okay. Now, one thing I want to say is this presentation did something funky with some of these equations. Okay, so like that's an image that's not supposed to be an image. That should be an equal sign. Okay, and it really should be a proportionality sign. Okay, so what this is supposed to be is proportionality sign. So when you see this little fish symbol, okay, it has a name, but when you see this symbol, it means proportional. Okay. So what they're trying to say here is that pressure is proportional to 1 over volume. Okay, so what this means, what they're trying to say here is that as pressure goes up, volume goes down. Okay, they call this an inverse relationship. Okay, that means as one goes up, the other one goes down. Okay, so if you had a container that's flexible, okay, this means the container is able to move. Okay, we're not talking about glass or metal containers, those things can't move. Okay, but if you had a container like a balloon, so pretend we have a balloon, balloons can expand or they can shrink. Okay, so if you had a balloon and if you increased the pressure on the balloon itself, if you increase like or outside the balloon, not inside the balloon. Okay, so you have a balloon, the balloon has air in it, whatever. If you increase the pressure outside, right, if you increase the pressure outside of the balloon, the volume is going to go down. Okay, if you decrease the pressure outside of the balloon is going to expand and get larger. Okay, so this is Boyle's law. Okay, pressure and volume are inversely related, and they give you an example here. Okay, so we have a container here. Okay, this is what we're looking at. We have a container here. The volume is 2 liters, and it has a pressure of 32 millimeters of mercury. We talked about that yesterday in the barometer. Okay, so the pressure is 32 millimeters of mercury. If we then double the volume, so we expand the container, we made the container bigger. If we make the container bigger, we doubled the volume and the pressure got cut in half. Okay, so this got doubled, so times 2, and then the pressure therefore got smaller. It got cut in half. Okay, it got cut in half. So that is Boyle's law. Okay, pressure and volume are inversely related. As one goes up, the other one goes down. Okay, and how you can explain this is think about the container. If you have the same amount of material, this is why you have to assume temperature and moles are constant. If you have the same amount of material in both containers, but one container is smaller than the others, remember pressure has to do with the collisions. Since this container is smaller, the molecules are going to run into the walls more often. Okay, so they're going to be colliding with the walls more, and that means you get a higher pressure. If you make the container bigger, you're going to have less collisions on the wall, which is going to give you a lower pressure. Okay, so that is Boyle's law. Okay, you see this K here. Yeah, they have a K in the equation. Okay, I would tell you not to worry about it and just think of the equation as V is equal to 1 over P. You can ignore the K. What the K is a constant. It's a proportionality constant, they call it. And that just accounts for different adjustments. Okay, so depending on the conditions, the K will change, but K is just a number. It's just a value. It is a constant, meaning it doesn't change. And what's important is the 1 over P part. Okay, so as volume goes up, P goes down in order to keep things constant, and vice versa. As one goes up, the other one goes down. That is Boyle's law. Okay, you have an inverse relationship. Okay, and here they have a little graph for you. As volume decreases, pressure goes up. As volume increases, pressure goes down. Okay, that's the relationship between them. Okay, that is Boyle's law. Okay, now we're going to get to the next one, volume and temperature. Volume and temperature is Charles. Okay, volume and temperature, they do not have an inverse relationship. Okay, you would call this directly proportional, meaning they go up together. Okay, as one goes up, the other one goes up. If one goes down, the other one also goes down. Okay, so this is Charles' law. It's the relationship between volume and temperature. And again, we are assuming that we are keeping pressure constant and moles constant. Whatever two variables we're looking at, we're keeping the other two the same. So in this case, we're looking at volume and temperature. We are keeping pressure exactly the same and moles exactly the same. Okay. And again, we have two containers. And again, assume the container is able to expand. Okay. So first container, volume is 2 liters. Okay. And the temperature is 200 Kelvin. Okay. And then let's say we decide we're going to heat up the container. We're going to double the temperature. So now the temperature is 400 Kelvin. What happens to the volume? The volume also expands and goes up to double as well. So if you double the temperature, you also double the volume. Why does that happen? Well, if you remember from the first day of gases, we talked about how the particles have kinetic energy and they're in constant motion. And how much kinetic energy they have is related to their temperature. So think about it, by doubling the temperature, I'm not going to say we doubled the kinetic energy because that relationship isn't necessarily one-to-one, but let's pretend that we did, okay? So you double the temperature, so you doubled the kinetic energy. So since the molecules now have more energy, that means they're going to hit the walls harder. And so if they're hitting the walls harder, the walls are going to expand, okay? They're going to expand until they get to a point where now it's equilibrium again, okay? So you increase the temperature, you made the molecules faster and hit harder, and because they're faster and they hit harder, they expand the container, okay? So that's the relationship between volume and temperature. If you increase volume, you increase temperature. Again, assuming we're keeping pressure and moles the same, okay? Because they're in most cases you can adjust more than one thing at a time. All four of them play a role together. They're all interconnected, okay? But we're looking at two sets at a time, okay? So as volume goes up, temperature also goes up, okay? And how you can think about this is if you want to compare. So in this case, we have V1 and we have T1, okay? So think about it. So volume V1, what is it? Oh, V1 over T1, right? I think that's what it would be. Yeah, V1 over T1 is equal to V2 over T2. Okay, so if you double, let's say we wanted to find a new volume. We want to find V2. Okay, we want to find V2. So if you want to find V2, we have to get V2 by itself, which means we have to double, or not double, we have to multiply by T2. So then you get V2 is equal to V1 T2 over T1. Okay. And then if you look at this, let's look at this, the part I'm going to circle in green. Okay. So think about this as V1 over T2 over T1. I mean, V1 times T2 divided by T1. And just look at this part, T2 over T1. So let's call this is the ones, and these are the twos. T2 is 400, T1 is 200. 400 divided by 200 is 2. And then V1 is 2, and then 2 times 2, you get 4, okay? So what this is showing you here is that the volume change is dependent upon the temperature. So if T2 went down, then volume 2 would go down. If T2 goes up, then V2 goes up, okay? So think of V1 and T1 are the originals, and then the V2s are what you're trying to find, okay? And this is the relationship you were trying to get. If you want to account for changes, this is the equation you would set up, okay? If you want to convert it from one to the other. Okay, and you would do something similar with the pressure above over there. Okay, and that's and then they're showing you here as temperature increases, volume increases. That's Charles' law. Okay, next is Avogadro's law, which focuses on volume and moles. This one's a little more intuitive. This one's a little more straightforward, more common sense. So this time we're looking at volume and we're looking at moles. Again, we're keeping temperature and pressure the same. Okay, we are assuming temperature and pressure are exactly the same. Okay, what you have here is, so we have 4 moles of gas, and then we double it to 8, so times 2. What's going to happen to my volume? Well, it's also going to double. Okay, again, pretend that the container can expand. If you shove more people in a room, they're going to be uncomfortable, right? So if possible, what would they do? They would make the room bigger, okay? Because they want more room. No one wants to be that close together, okay? So here we have this small container. If we suddenly double how many people are in there, if we suddenly double how many molecules are in there, they're going to be uncomfortable. We increased the pressure temporarily. But in order for pressure to be constant, the room has to expand. So that's exactly what happens. If you shove more material into a small container, if possible, the container is going to expand to account for the extra molecules that are there. Okay. So as you increase moles, you increase volume. That's the relationship between them. Okay. And if you wanna account for the change, you would do the same thing with that we did earlier. So V1 N1, where N is moles, is equal to V2 over N2. Okay, the ratio has to be the same. Okay, that's what this means. Okay, the relationship between V1 and N1, or the ratio, has to be the same as the new one. Okay, because all the ratio has to stay the same. That's how we find what the new change is. Okay. So that's Avogadro's law. As volume goes up, or as moles goes up, volume goes up, and vice versa. Okay, and they have a little graph here, Avogadro's law. Moles go up, volume goes up. And then last but not least, we have pressure and temperature. And we are pretending that moles and volume are constant. So if volume is constant, that means now instead of a stretchy container, we no longer have a stretchy container. Pretend we have a metal container. The container cannot expand. It can't shrink. Okay, we have a metal container. Okay. We double the temperature. Okay. What happens if we double the temperature? If you increase the temperature, you gave the molecules more energy. They're going to go faster, which means they're going to hit harder. So what if the container can't move, what's going to be higher? The pressure. Okay. If you increase the temperature, you increase the pressure. You gave the molecules more energy, they're going to hit the walls harder. There's nowhere for them to go. The container can't expand, so the energy can't go anywhere. Okay, so then it just stays inside, and you have an increase in pressure. Okay, you have more energetic collisions. Okay, so as P goes up, T goes up, and vice versa. T goes up, P goes up. They go up together. Okay, they are directly proportional. So four out of the out of the four laws, okay, out of the four laws, the only one that is inverse was the first one. Okay, pressure and volume is the only one that's inverse, meaning as one goes up, the other one goes down. Okay, the rest of them go up together. Okay, and again, so recap: pressure and volume. As pressure goes up, volume goes down. Why? Because the container is getting smaller. Okay, and or in order for pressure to go up, the container has to get smaller because we're keeping temperature the same. So energy is the same, and the amount you have of each is the same. Okay, so as pressure goes up, volume goes down. The next one is volume and temperature. Assuming we're keeping pressure the same, if you increase temperature, volume has to go up. The molecules have more energy, and so they expand the container. Okay, more energy, they stretch the container out to account for that. The next one is volume in moles. If you shove more molecules in a small container, they're going to want to spread out. And so to account for that, if we want to keep pressure the same, you have to expand the container. And then pressure and temperature, if you increase temperature, the molecules are going to hit harder. They're going to hit the walls harder. So that means an increase in pressure. Okay. Tomorrow, when we talk about the ideal gas law and we combine all of them together, it'll make more sense. Because looking at them independently, they kind of make sense, but I know it can be a little confusing. But when we combine all of them together, it'll make complete sense. Okay, and that's it's called the ideal gas law. It's how gas behaves under ideal conditions. Okay, and this is a summary. This is a summary of all the laws we just looked at. Okay, so P and V is the only inverse relationship, meaning as one goes up, the other one goes down. Okay, V and T, volume and temperature. Okay, as one goes up, the other one goes up. The same for the rest of them. Okay, these are all direct relationships. Okay, those are your four laws. And all together, they combine to make the ideal gas law. Now, these are the equations you would use if you wanted to make a prediction. So I was talking about these laws are used to make predictions, okay, to make changes. So let's say you had a gas in a container, okay, you want to move it to a new container, but you don't know what's going to happen to the gas when you move it to a new container. What can help you figure that out is these laws, okay? So let's say we're looking at Boyle's law. I don't want to change the temperature, okay? I'm not changing the temperature and I'm not adding any new gas. What's going to happen when I move this volume to a new container? Maybe the old container is rusting, okay? It's rusting, it's getting old, it's about to break. I got to put it in a new one, okay? What's going to happen to the gas? You would use this law to figure it out, okay? P1V1 is equal to P2V2, okay? What I want you to notice is that all the ones that are direct, okay, they're in fraction form. All the ones, or the only one that's inverse, it's not in fraction form. It's set up like this. And the reason is because what you want to do is you want to set them all up so that you get P2 by itself, okay? And let me do that real fast so you can see what I mean. So I'm going to solve for a 2 in all of them. In this case, I'm going to solve for P2. If I do that, you get P2 is equal to P1 V1 divided by V2. This one, you're going to get V2 is equal to V1 N2 over N1. This one, you're going to get V2 is equal to V1 T2 over T1. And then Lusak's law, you're going to get P2 is equal to P1 T2 over T1. Okay. I'm going to circle all the ones in green that I want you to focus on, or the part of the equation I want you to focus on. Okay. Look at this. So again, pretend that if it has a 1, that's the original. 1 is the original, 2 is the change. Okay. 1 is the original, 2 is the change. So for this first one, let's say I'm moving it to a new container. I want to find what the new pressure is. It's V1 over V2. Okay, V2 is the new one. So if I know the volume of the new container, I can figure out what the new pressure is going to be. And if you have a new container, then obviously you're going to know what the volume is. If the volume of the new container is bigger, bigger denominator means smaller overall number. Okay, so if V2 is larger than V1, if the new container is bigger, pressure is going to go down. If the new container is smaller, pressure is going to go up. Okay, V1, and I want you to focus on this for a reason, because the volumes is the obvious thing to look at. For Avogadro, look at the moles. For this one, 2 is on top. All the other ones, 2 is on top as well. The only one that's inverse is the only one that has a 2 on the bottom. The rest of them have the 2 on top. Okay. For Avogadro, if the new number of moles is greater than what you had originally, volume is going to go up. That makes sense. For Charles' law, if the temperature increases, you're going to get an increase in volume. That makes sense. And for Lusak's law, if your new temperature is greater than the original, pressure is going to go up. Okay. The only one where if the new container is smaller, you get a higher pressure. If the new container is bigger, you get a smaller pressure. Okay. The things highlighted in green are the relationships that are the most, that make the most sense to look at, to make sense of the loss. Okay. And this is what you're going to use in the worksheet to answer some of the questions. Okay. These exact equations are what you're going to end up solving for. Okay. You may not always be solving for, well, actually, no, you can always set it up like this. Okay. You can always set them up the way I set it up. And let's do an example. Okay. Do they have any good examples before it gets to these, before we get to the worksheet? Matter of fact, no, I'm not even going to bother with these examples. Let's just go to the worksheet. Okay. How are we doing on time? Okay. 22 minutes. Okay. That's kind of long. Okay. So I want to wrap this up before we get to 30. Okay. But those are your 4 laws: Boyle's, Avogadro, Charles, and Lusak's, and they all combine together to make the ideal gas law, which we will look at tomorrow. Okay. Well, okay. Worksheet. It's all multiple choice. Okay. 10 multiple choice questions. I do believe all of them are going to require a calculation. Okay. All of them are going to require some type of calculation. Okay. So let me do number 1 and number 2 with you. Okay. So number 1, we have a sample gas. They give you the mass initially at 4 atmospheres, and this was compressed from 8 liters to 2 liters at constant temperature. After the compression, the gas pressure was blank. Okay. So they give you the mass. Okay. The mass is irrelevant. The only thing that's important is that if you read through it, the mass doesn't change. Okay. If it doesn't change, that means we're not adding any new material. Or in other words, moles is constant. Okay. So moles is constant, and they also tell you temperature is constant. So N and T are the same. We are comparing pressure and volume. Okay. So we are looking at P and V. Which equation looks at P and V? That's Boyle's law. So this is the one we're looking at. After the compression, so we are looking for P2. Okay, so we are looking for a new pressure. Okay, we are looking for P2. So P2 is equal to P1 V1 over V2. Okay, P2 is equal to P1 V1 divided by V2. Okay, so what is P1? P1 is initially 4. What is V1? V1 is 8. And then V2 is 2. Okay, you're going from 8 to 2. Okay, so that's how I know the 8 is my 1, the 2 is my V2. Okay, you plug all the numbers in. 4 times 8 is what? 4 times 8 is 32. And then 32 divided by 2 is what? 16. Okay, so number 1 is 16E. Okay, number 2 looks at what? Are we looking at? Okay, we have a gas. This one, okay, this one's the same law. This one's Boyle's law again, so I'm not gonna do it. It's the same equation. Let's do one that's a little different. Okay, so I'll do number 1. What's one that's a little more difficult? Okay, because I don't want to do the hardest one because then I'm taking away all the fun. Okay, let's do number 7. Okay. A balloon originally had a volume of 4.39 liters at 44 degrees Celsius and a pressure of 790 or 729 torr. The balloon must be cooled to blank to reduce its volume to 3.78. Okay. Assume we have constant pressure. Okay. So we have constant pressure, and it doesn't say anything about moles changing, so we assume we have constant moles. So P is the same, N is the same. We are looking at the relationship between volume and temperature. Which one's volume and temperature? That's Charles' law, okay? So we are looking for V2, okay? So the equation we're going to be using is V2 is equal to V1 T2 over T1, okay? What we're looking for, it says the new balloon must be cooled to what temperature to reduce the volume, okay? So we know V2 already. We know what we want. We know the original, and we know the original temperature. What we want to solve for is V2. So actually, I need to rearrange this equation, okay? I need to rearrange this equation to get T2 by itself. If I do that, you get that T2 is equal to V2 T1 over V1, okay? So then all you got to do now is plug your numbers in. So then T2 has to equal V2. V2 is going to be 3.78. That's the new volume that we want. Okay, time. What's the original temperature? The original temperature is 44 degrees Celsius. Okay. Now, side note, okay, normally when you're using these types of equations, the temperature usually has to be in Kelvin. Okay. Matter of fact, I'm pretty sure it does have to be in Kelvin. Okay, so let me do that. Okay, the reason is the ratio is not going to be the same. Okay, I'm 99% sure the temperature has to be in Kelvin. Okay, because so the reason it has to be in Kelvin, well, no, actually it doesn't. It doesn't. Okay, I'm confusing something else. Okay, so it's fine the way it is. Just plug the numbers in as normal. Okay, so 3.78 times 44 divided by what is the old volume? Okay, 4.39. Okay, plug your numbers in. Let's see what we get. 3.78 times 44 divided by 4.39. And we get 37.88, which rounds off to be this. Okay, so in order to get the volume down to 3.78 liters, we need to cool down the temperature to 38 degrees Celsius. Okay, so that's another way you can use these laws. If you don't want to, if you know what volume you want, you can figure out what temperature you need. Okay, assuming the container can expand. Okay, so that's number 1 and number 7. Okay, the rest of them follow that same pattern. Figure out what law it is, what equation you have to use, and plug the numbers in. Okay, but that's it for today, ladies and gentlemen. Happy Wednesday. I wish you all the best. Take care. Please stay safe. Again, things are kind of crazy right now. But Godspeed. God bless. Take care. Have a good one.